Today, I will be demonstrating and explaining simple harmonic motion. Simple harmonic motion can be defined as periodic motion where an object moves back and forth around a certain point. The force that brings the object back to that central point is proportional to the displacement from the point. Put simply, the displacement of the object moving away from the central point is the same as the displacement of the object moving back towards the central point. A sinusoidal equation looks like this. Y equals A trig bx minus c plus d, where trig determines the type of graph, either sine or cosine. A determines the amplitude of the graph, where amplitude equals absolute value of A. D determines the vertical shift of the graph, where vertical shift equals the value of D. Phase shift can be found with C divided by B, where phase shift equals C over B. And period can be found with 2 pi over B, where period equals 2 pi divided by B. All of this will change the position of the equilibrium, as well as changing the length and distance from the equilibrium. The model that I will be using to represent simple harmonic motion is a pendulum. Well, it's a yo-yo attached to my ceiling fan. I will demonstrate by swinging it back. Try that again. What I have done here is added red lines to better explain the motion. The middle line represents the equilibrium, and the 2 lines on the sides represent the amplitude. The yo-yo swings continuously back and forth, passing the equilibrium and stopping at the amplitudes before changing direction. This is akin to how a point on a sine or cosine graph would move, continuously moving back and forth as it moves along the line. Based off our model, amplitude is 75 degrees, period is 2 seconds, there is no phase shift, and the displacement is 0. The amplitude was found by measuring the angle between the equilibrium and the furthest point away from the equilibrium. The period was found by measuring the time it took the yo-yo to swing from its starting position back to said position. There is no phase shift because the yo-yo started from its highest point, and the displacement is 0 because that is the position of the equilibrium. When referring to a trigonometric model, each part of the equation y equals a cosine bx minus c plus d affects the graph. Amplitude is found with A, which determines how far the furthest point is from the equilibrium. Displacement can be found with D, which represents the object's position from the equilibrium. The period can be found using C over B, which affects the horizontal stretch or compression of the graph. And the phase shift can be found with 2 pi over B, which affects the horizontal position of the graph. For our model, all of these same principles would apply. Now for the equation that represents our model. With the data we collected, we can create a sinusoidal equation that represents the simple harmonic motion in our model. So we have y equals a cosine bx minus c plus d to y equals 75 degrees cosine 2 pi over 2x. A was found by using the amplitude. B was found by using period equals 2 pi over b and solving for b. Since there is no phase shift, c is 0 because it starts at the maximum height away from the equilibrium. And since the equilibrium is at 0, displacement is also at 0 because the pendulum is hung straight down. And that is my video. Most of my research was done on my own, but I did have some help from ChatGPT.